Welcome to Lesson 4D, Hearing and Noise, Part 2. Today we're going to talk primarily about multiple sources, and then we'll look at noise standards from OSHA and look at these so-called colors of noise. Let's look at multiple sources first. What we're talking about is, suppose here's your ear or a microphone, and there's more than one source. So there may be a source here, another source here, and another source here. They all have different radii. RA, RB, RC, some of them may be closer than others. They all have different levels of sound intensity. In general, we'll have J sources. So little j is 1, 2, 3, up to capital J. So how do you do something like this? Well, first you have to calculate LPJ, sound pressure level, for each source. And then there's a cool little formula. LP is the total, what you hear from all of these noise sources, is 10 log 10, again this is log 10, not natural log, of sigma j equal 1 to capital J. So we're going to sum over all of these. And then what's inside the sigma is 10 raised to the exponent LPJ over 10. Take each LPJ, divide by 10, use that as an exponent for 10 raised to the LPJ over 10. And then you sum those up, and then you take 10 log 10 out of that when you're all done. Let me do an example. There's a man standing between two noisy machines on a concrete floor. That means it's a hard surface reflection, no walls nearby. So that tells us that Q is 2. Machine 1 has an acoustic power of 0.4 watts. There's 1 meter to the man's right. Machine 2 has acoustic power of 0.5 watts, 2 meters away to his left. Estimate the sound pressure level. Now notice that these are acoustic power in watts. They're not LW. So first we have to calculate LW for each source. LW1 is equal to 10 log 10 of W1 over W0. This turns out to be 10 log 10 of 0.40 watts over 10 to the minus 12 watts, 116.02 dB. I said to round off to the nearest dB, but you don't do that for any kind of intermediate steps. And similarly, LW2 is same thing, except that's a 2 subscript, and then its power is 0.50 watts instead of 0.4. Everything else is the same, and I get 117.00 dB. Remember, these guys are independent of who's hearing. These are sources. We don't care who listens to this. These are set. Once we have those, we can calculate LP for each source. This is the sound pressure level. LP1 is LW1, 10 log 10 Q minus 11.0 minus 20 log 10 R1 over R0. Plug in the numbers. This, we calculated 116.02. Q is 2. The reactivity factor is 2 because there's a concrete floor with no walls. And then R1 was given as 1.0 meter. And this, of course, is also 1.0 meter. We get 108.03. I'm keeping 5 digits here for these intermediate steps. Similarly, LP2, you can go through the math to double check, 102.98 dB. And then now we use our formula, LP total equal 10 log 10. 10 to 108.03 divided by 10 is 10.803. And then this one, you divide by 10 in your head there, you get 10.298. You get 109.21 dB. Now I round off to the nearest dB. That's our final answer. A couple comments here. Due to the nature of sound, you can see that noise does not add up linearly. We have all these logarithms flying around. Our total is 109. Even though we have 108 from one of the machines and 103 from the other, but we certainly don't get 200 and some dB, we get only 109. It's not an average, it's not a sum, it's that more complicated formula. Here, where we have the man standing here, he's pretty close to this machine. Machine 1 is 108 dB. This one's further away, 103 dB. And so since he's close to this one, that one dominates. And if you've ever been in a plant where there's 2 machines running and you're close to one, you really hear that one loud, but you hardly hear the other one, even if it might be a louder machine, but it's further away. You don't hear it that much. The total is 109 dB, which is only 1 dB greater than that 108 was. I also want to comment that if we had carpeting or some kind of rubber mat or something on the floor, then Q would be less than 2. For example, suppose Q was 1.5 instead of 2. We recalculate, and you can do that for practice. You should end up with LP, the total being to nearest dB 108 dB, which is about 1 dB lower than what we got for our real case. I wanted to mention then noise standards. OSHA is the government agency that regulates noise. They have standards and they can give fines if you don't comply. ACGIH, they do not regulate, but they do have standards and they cannot give fines. So it's very similar to what we talked about previously. They just give recommendations. And in general, they're stricter recommendations than OSHA is, just like with the gases. There's a table in the book, and I have it also copied on the next page, where it lists both of these standards. In either case, the table was made such that the higher the noise level, the shorter the allowed exposure, and that's in hours. That makes sense. If you have a very loud noise, you can tolerate it for, say, 1 hour. If you have a quieter noise, maybe you can tolerate it for 4 hours before OSHA decides that this could cause damage. Remember, all these regulations are based on a 40-hour week, 8-hour day for a whole career, 25 years or whatever. So, you'd have to be exposed to this a long time before OSHA says you're going to have hearing damage. What happens, as I mentioned before, these high levels of noise will start to break some of those little cilia hairs in your cochlea. OSHA regs are based on every 5 dB increase in noise equal 1/2 of permitted time exposure. And ACGIH takes a stricter view. Every 3 dB up equal 1/2, I won't say permitted, but the recommended time exposure. So ACGIH is more strict. What I mean is this. Let's look at OSHA, and I'll use blue here for OSHA. We start at 80 dB, and they allow you to listen to a sound at 80 dB for 32 hours. So obviously in the 8-hour day, you're not going to be exposed to that. Then if we go up 5 dB, we take a factor of 2 down in exposure time allowed. So from 32 to 16 hours. You go up again 5 dB, you go down by a factor of 2. Again, factor of 2. So at 95 dB, you can only be exposed for 4 hours. At 100 dB, you can only be exposed for 2 hours, and it continues this way. ACGIH, I'll use green. 82 gives you 16. 85 is 3 dBs more, and they go down by a factor of 2. 88 is 3 dBs more than 85. They go down by another factor of 2. 91, add 3 to 88, and then they go down by a factor of 2, and it continues this way. So in any of these cases, say you have 100 dB, OSHA says you can tolerate that for 2 hours. ACGIH says only a quarter of an hour, 15 minutes. They're much more strict. Now, there's cases where you may be exposed to different sound levels for different periods of time. So if this is time in hours, and we start at beginning of the workday, end of the workday, 8 hours, and we plot the sound pressure level in dB. Suppose when you come in, there's no noise, and then maybe a couple hours later you have some noise at some level, and then you have a lunch break or something, and then you have some higher noise for a different time period, and then you have some more noise until you go home. And these are all at different levels, and they have different time periods.
I'm glad this dude got a break for lunch, man. I know you don't like to miss lunch, Joe.
So how do you do something like that? Well, OSHA defines a sound exposure parameter, and this is very similar to what we defined previously for gases. In fact, they even used the same notation, EN, the sound exposure parameter, defined as sigma J. J here is not the number of sources, it's the number of time periods. So in this case, you'd have 3 different time periods where you're exposed to some noise. TJ over TJ permitted. Suppose you were exposed to some 95 dB level for 3 hours. Well, the permitted is 4, so 3 would be TJ. That's what you're actually exposed. And this is permitted from the table. So you'd have a 3 on the top and a 4 on the bottom. The OSHA reg then is that if EN is greater than 1, it's a violation. If EN is less than 1, it's not a violation. And that is also the same as what we had with gases. And it makes sense because suppose you're exposed to, in my example, 4 hours of 95 dB, and that's the only thing you're exposed to all day long. It'd be 4 over 4, which is 1, so En would be 1. That would be a borderline case. And then if you have different time levels like this, you just keep going and calculate it. I'll do a quick example. Suppose you're exposed to 3 hours at 95 dB and 5 hours at 90 dB. Is that a violation? Well, first let's look at the table. And as I just showed you, TJ permitted is equal to 4 hours. For 90 dB, TJ permitted is 8 hours. It's 5 dB difference, so it's multiplied by a factor of 2. And so using our formula, En is 3, the actual time, over 4, the permitted time. These are both hours, plus 5 hours over 8 hours. The hours all cancel, of course, and we end up with 1.325, which is greater than 1. So we would say this is a violation. If workers were exposed to this every day, OSHA could come in and do some measurements, and then they would say you're not in compliance and be subject to a fine. People sometimes talk about the colors of noise. I give some references here. You may have heard of white noise. White noise is a flat power level at all frequencies, the same sound level over the entire spectrum. The problem is this: if you think about music and frequencies, suppose we start at 0 and then you have, say, 1,000. When you double that to 2,000, that's an octave. If you go up to 4,000, that's twice as wide. That's another octave. But the problem is the area of this is twice as much as the area of this. And one lower octave would be 500, so that would be half again. So if you put a constant power over this entire frequency spectrum, you are going to be putting in a lot more energy, a lot more power at the higher frequencies for each octave. And so you would hear the high noises much more than the low frequency noises. So it sounds like a kind of a hissing. Pink noise, what they do is they decrease the dB by 3 dB per octave. So they recognize that, hey, I'm going to hear these high frequencies more, so I lower the level. And they do it in a kind of a linear fashion on this log scale. This log scale is 100, 1,000, and 10,000 hertz. And so it goes down by 3 dB every octave. And so you'll hear this as a lower sound, kind of like a waterfall. And then there's also something called brown noise, which goes down minus 6 dB per octave. And so that will give you even more sound in the lower noise level. It sounds more like a rumbling or a wind blowing rather than water falling, not as much high notes. Here's the actual signals of white noise, pink noise, and brown noise. And these are the spectral densities.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3.